Inside silicon, the technology behind everything. Powered by Semionix.
Okay, so you've heard the buzz, right? Chiplets. They're everywhere. Everyone's talking about them as the future of how we design silicon, and for good reason. They promise better performance, way lower manufacturing costs, and this incredible new flexibility. But, as any engineer who spent time in the trenches will tell you, there is absolutely no such thing as a free lunch. It just doesn't exist. So the real question isn't whether chiplets are powerful. We already know they are.
The real question is this. What's the catch? What are the hidden trade-offs we're making? In this explainer, we're going to peel back the marketing layers and get right into the tough engineering compromises that are at the heart of this amazing technology.
To really get it, we have to start with how things used to be done. For decades, this was the gold standard, the monolithic chip. Think of it like a massive self-contained city where everything, all your CPU cores, your GPU, your cache, your I/O, is built on one single gigantic foundation of silicon.
But we've been slamming into a wall with this approach, a big one. As we try to make these silicon cities bigger and bigger, a couple of huge problems pop up. First, yield. Imagine baking a giant wafer-thin cookie the size of a dinner plate. If you get one tiny crack, one single microscopic defect, the entire thing is ruined. That's a massive financial loss. And second, we're literally running out of room. We're hitting the physical size limits of the machines that make the chips. And that's where chiplets come in, as this really elegant solution. Instead of one giant city, we build a collection of smaller, specialized districts, or chiplets, and then connect them all with a super high-speed transit system. It's a modular approach designed to get around that monolithic wall. But how, exactly? And more importantly, at what cost?
All right, let's dive right into our first major trade-off. This one is fundamental. It's the constant battle between raw communication speed and the amazing scalability that chiplets give us.
On a monolithic chip, data just zips around on these super short on-silicon highways. It is incredibly fast. But with chiplets, that same data has to physically leave one piece of silicon and travel over to another one. That journey is just inherently longer and way more complex, and that introduces delay. We call it latency.
And you can see that journey right here. The best analogy? Think about talking to someone in the same office building versus talking to someone in a building across town. In the same building, it's quick, but to get a message across town, it has to go down the elevator, out the front door, across the street. Every single one of these steps, crossing micro bumps, traveling through an interposer, adds a tiny bit of delay. And in high-performance computing, those nanoseconds add up fast and create a very real performance penalty.
So that brings us to the money. This second trade-off is a huge economic one. We're weighing the incredible benefit of better manufacturing yield against the brand new and very steep cost of advanced assembly. Now this right here, this is probably the biggest reason chiplets are so popular. On the left, one tiny defect and the whole expensive chip goes in the bin. A massive financial hit. But on the right, with chiplets, that same defect only takes out one small, relatively cheap chiplet. The rest of the parts are perfectly good. This just massively improves your manufacturing yield and saves a ton of money. But here's the big catch. All that money you just saved on throwing out bad silicon? Well, a huge chunk of it now gets poured right back into advanced packaging. Stitching these chiplets together with incredibly precise technologies is super complex and really expensive. I mean, for some of these high-end AI chips, the cost of the package can actually start to rival the cost of the silicon itself. It's a completely different way of looking at cost.
Okay, let's move on to our third and, I think, most fascinating compromise. This is where we pit the incredible design freedom that chiplets give us against the absolute mountain of engineering complexity they create.
This is where the magic of chiplets really shines. It's a concept called heterogeneous integration. It means you can use the absolute best, cutting-edge, most expensive manufacturing process,
say 5 nanometer, only for the parts that really need that speed, like your CPU cores. Then, you can use older, more mature, and much cheaper processes for other things, like your I/O. It's all about using the right tool for the right job, and it is just incredibly efficient.
But, and you knew there was a but, getting all these different parts built in different factories with different physical properties to all play nicely together, that is a monumental engineering challenge. Every process node has its own electrical and thermal quirks. You have to design these ridiculously intricate power delivery networks, make sure signals don't get corrupted moving between chiplets, and get the timing of the entire system to sync up perfectly. All that amazing flexibility comes at the cost of just immense system-level complexity.
And this complexity isn't just a puzzle for the designers to solve. It actively creates new places where things can go wrong. The interconnects between chiplets can suddenly become a data bottleneck, starving your super powerful cores. And then you have to validate the long-term reliability of this whole complicated system, which is a whole new world of engineering pain.
So after looking at all these different trade-offs, a really clear picture starts to emerge. It's not about finding some perfect, magical solution. It's about finding the right balance for the problem you're trying to solve.
And this table just lays it out perfectly. It's a balance sheet. For every single powerful advantage that chiplets bring to the table, there is a corresponding and very significant trade-off. You get much better yield, but you pay for it with high packaging costs. You get awesome modularity, but you introduce latency. You get incredible flexibility, but you have to wrestle with a mountain of complexity. This right here is the day-to-day reality of modern chip design.
This really says it all, doesn't it? Progress in our field isn't about finding some silver bullet that solves everything. It's about engineers making smart, informed decisions and intelligently managing all of these competing demands.
And at the end of the day, this principle, the art of balancing these competing constraints, is what's going to drive the entire semiconductor industry forward. The next generation of mind-blowing processors for AI, for science, for everything. They're going to be born from engineers successfully navigating these exact trade-offs.
So that leaves us with a final thought to chew on. As these individual chips evolve into what are basically entire systems on a single package, what new, unforeseen challenges are waiting for us? And where will we find the next great engineering compromise?
Inside Silicon, the technology behind everything. Powered by Semionics.